We're not having a hunting video.
Or that could be Swedish.
No, I think it's Swiss.
That's not a Swedish accent.
So last time we kind of did an exploratory activity,
Not a Swedish accent.
France.
and this time we're going to take that exploratory activity and apply it.
It's crackers on fake cheese with fake
Ham.
Oh dear, it's
Or
fake ham.
salami.
That's the worst fake pepperoni I've ever seen.
So our goal today
That was a major fail.
is to find the extreme values. Oh, I forgot to change the objective. Sorry, extreme values of a function using the extreme value theorem.
Oh,
I was going to do
Damn.
both, but then I decided
Good thing I didn't
like
write
how
that
to.
down. I might have had to erase or something.
So that's our goal. We're going to learn about the extreme value theorem today. That is one of the big three. You remember we learned about intermediate value theorem in like the first chapter. You may have forgotten it by now because it's a very short portion of the chapter. But extreme value theorem is used pretty often. In fact, I do have an AP free response test question that will be part of your homework that has extreme value theorem. So let's go over our conclusions from last time, the whole point of our activity from last time. So if f of x has a max or a min, we learned something from that information. We learned something about the derivative from that information. So when f of x has a max or min, what do we know about the derivative of that function?
it is a x equals.
F prime of x equals 0. The slope equals 0. What else? What was another possible option? That covered our, if we had f of x, slope being 0 here. What was another option? What if I had
It does not exist.
does not exist? So if f of x has a max or a min, then f prime of x equals 0. Or f prime of x does not exist. That was a guarantee, ironclad, must happen. If you have a max or a min, you must have the derivative equal to 0, or the derivative does not exist there. The other direction wasn't as ironclad. If f prime of x equals 0, or f prime of x does not exist, then f of x has possible maxes or mins. It might be a max or a min. Which is still good information for us, because that gives us, instead of having to choose from all x values, we can limit it to how many x values are possible maxes and mins. So if f prime of x equals 0 or does not exist, then f has possible extreme values. So there's actually two ways for us to label extreme values. We call some extreme values local extrema and some global extrema. Extrema is just the plural of extreme values. Extrema means max or min. So another word we might use is relative extrema or absolute. So local and global, or relative and absolute. And there is a difference between the two types. They're fairly similar, but there is a little bit of a difference. So a local extreme value only occurs on a small area of the graph. So it's the highest or lowest point over a small interval. Now, math notation wise, that gives us the general idea, but it doesn't really give us the math notation. If I were to say that it's the highest point, or no, the lowest point, I would say f of x is less than or equal to f of c for all x on some open interval. Basically the same thing as what we just said, but a little bit more math notation instead of general idea. So actually that is a maximum, not a minimum. F of c is bigger than everything around it. If I wanted to say minimum, I'd just flip that. F of c is less than everything around it. So global extreme values just our highest and lowest points over the entire domain. So local can happen picture-wise. This would be a local max right here. Do like an interval around it just to show why is that only local and not global.
Because to the right of it,
This graph goes up higher than the maximum. It doesn't mean it's not a maximum for its little particular area, but it's not the global maximum. It's not the best or the highest overall. Whereas global, that point would be a global maximum because it's the highest point over the entire domain. There is no other point on this graph that is higher. So then critical points are used quite a bit when we try to find local or absolute maxes and mins. A critical point is we're going to use the more mathy definition. A point in the interior of the domain where f prime of x equals 0 or f prime of x does not exist. So basically, in the non-mathy version, what we're saying is we're finding the possible candidates for maxes or mins, the possible extreme values, and we find those possible extreme values by setting the derivative equal to 0 or finding where the derivative does not exist. So a critical point is not guaranteed to be a max or a min. There are those certain situations where we could still get a critical point and not have it be a max or a min. Usually the cubic functions are the best example of that. Yeah, this would have a slope of 0. No, it's not a max or a min. So these are only finding possible extreme values. So when we're on a closed interval, today we're going to be working specifically with closed intervals. What do I mean by a closed interval? What do we mean by a closed interval?
Only a certain part of the graph.
Only a certain part of the graph, basically. So when we say closed interval, we say from some x value a to some x value b, but they must have brackets because we're including a and b. So we're looking at just one piece of a graph. So when we are on a closed interval, we are guaranteed an absolute maximum and an absolute minimum. So let's see why. If I'm only doing a piece of a graph, they don't need to be super nice. You don't have to draw even the units in, but I would draw the graphs themselves. So what would our maximum be on this graph? I might say even 4-ish. Oh,
yeah, sorry.
you're
I was
talking
like-
about the y value. Okay. You're right. 6.5-ish. It occurs at 4. I was just looking at 6.5 on the x-axis. Yes. So that's about our maximum. What about our minimum?
It's right where it is.
This right endpoint is our minimum. Even though there's nothing going on with our graph after that, our endpoint can count as a minimum. So we're guaranteed a max or a min because no matter what our graph looks like, even if I'm a straight line still has a max and a min because our endpoints sit at a low spot and a high spot. And I guess I should say on a closed interval with a continuous function. This would not work if we were not continuous. So it must be continuous. Even, we really only needed 3 of these. I don't know why I made 4. Even if I have a line like this. Ugh, that is not at all straight. Let me try that one more time. I still have a max and a min. They happen to be the same value, but this is still considered a max and a min. It's greater than or equal to all the points around it, and it's less than or equal to all the points around it because it's equal to. So when we are on a closed interval, because those endpoints could act as our max or a min, we are guaranteed a max and a min. It's a guarantee. So this concept is called the extreme value theorem. If f is continuous on a closed interval, and that's so important that we remember it's a closed interval. Right now that won't seem hard because that's all we're working with. But when we get to open intervals, we'll often forget that a closed interval has different rules. Just because you do the process fairly similar to an open interval, with only one slight difference. So f is continuous on a closed interval a to b. Then f has both a max and a min on the interval. So So this is one of our important theorems of calculus. I usually call it EVT for extreme value theorem. So we have enough information now to take a function on a closed interval and find its max or its min. That's our goal. Actually, its max and its min. That's our ultimate goal today, is to actually take a function on an interval, find its max, find its min. So usually it will tell you to find the extreme values of the function. It might say find max or min, it might say find relative extrema, it could say find absolute extrema. In this case, since we're on a closed interval, it would have to be absolute extrema, not local. We're guaranteed an absolute maximum and an absolute minimum. And then it will give you an interval. Maybe written like this, maybe written like that. Could be written in either format, interval notation or set notation. But again, we must be on a closed interval right now. We're only working with closed intervals. So it is possible for our endpoints to be the maxes or mins, but in the first graph we saw, it was possible for an interior point to be the max or the min. So we still have to check those interior points. We need to find all the possible candidates. Right now I know 2 possible candidates right off for my max and my min. What 2 values could be the max or could be the min? 2 and 5. They gave us those endpoints on the interval. Those are possibilities, but I still need to find the inside candidates. So our first step is set f prime of x equal to 0 and find where f prime of x does not exist. That process finds me my critical points, my possible maxes and mins inside the interval. So if we're going to set f prime of x equal to 0, what do we need? Because right now I only have y, f prime. Take the derivative. This one's straightforward. Power rule. Be careful, because it's a common mistake, I still do it, to just write 3x instead of 3x squared. Especially when it's to the third. I don't know why we forget that most often. So 3x squared minus 2. And what did we want to do with this derivative? Set it to 0. Now on this one, I have a polynomial. So where does a polynomial not exist? Are there any values that I could not plug in for x? Polynomials are continuous everywhere. The types of functions that might give me trouble are rational, so fractions. If you're dividing, you can't divide by 0. Radical, we can't square root a negative. Piecewise functions often give us our jumps or holes or anything like that. So polynomial, there's nowhere this does not exist. We're good to go just solving for 0. So we get 3x squared equals 2. Divide by 3. Square root. So x equals square root, or plus or minus square root of 2 over 3. Now, one of these I can throw out immediately. Which one can I get rid of immediately? The negative one. We definitely don't have any negative values. So at the critical points, they might not even be in the interval. So we need to check if the critical points are on the interval. Usually just write CP for critical points. So negative square root of 2 over 3, definitely out, not on the interval. What about positive square root of 2 over 3? Is that going to be between 2 and 5? Emma's shaking her head no. Why do you think not? You're right. It's not on the interval.
I just thought no.
Okay. Well, let's think about our square root values. What do we know is the closest perfect square to this? 1. And we know 2/3 is less than 1. So what's the square root of 1? 1. That means square root of 2/3, it's going to be less than 1. It has to be. Square root of 1 is 1, square root of 2/3, which is smaller, when you square root it, is going to be a smaller number. Well, we know 1 is less than 2, so square root of 2/3 is also not on the interval. And it's possible they might give this problem as a no calc, and you would have to use the logic like that. You know, square root numbers, the square rooting process doesn't change the order of what's biggest to smallest or smallest to biggest. Okay. So we don't even need to worry about these critical points on this one. It's a possibility, but not necessarily. So once we found all our possible points, we have our endpoints 2 and 5, we checked our critical points, neither of them were on the interval. We plug all points into the original function. So when I say all points, I mean endpoints and critical points on the interval. Into f of x. We don't know which one's the max or the min until we plug it in and see which one's bigger, which one's smaller. So we take just 2 and 5. Those are our only 2 points that we didn't throw out. We find f of 2 and f of 5. Extend this page and move this down. It's not in the way. So since I just moved the other one down, usually we just stack them in a row so that we can compare it easily. So f of 2, our function was x cubed plus 2x, no, minus 2x plus 4. So we're plugging it into f of x. We're finding the actual y values of the max or the min.
So what would change if those points were to exist on the interval?
The critical points?
Yes.
Nothing, we would just have more to plug in. We'd
So
also
you had to
have
put them on.
f of square root of 2 over 3, f of negative square root of 2 over 3. And then just only 2 of them are your final answer. So we get 2 to the third minus 2 times 2 plus 4. That is 8. Just 8, isn't it?
Yeah.
Then we plug in 5. 5 to the third minus 2 times 5 plus 4.
It's 119.
119. So which one is our max? Which one is our min?
F of 5 is the max and F of
So max is f of 5. min is f of 8. No, sorry, f of 2. So our highest value was at 5. Our lowest value was at 2. And we have found our maximum and our minimum. So I'm going to have you guys try one. Y equals x to the 2/3. Oh, I didn't give you an interval. That
Can you
would
scroll
be
up a
important.
second so I can finish writing that down?
Let me look up the interval. Sorry, I did not include it. But we cannot do these without a closed interval, so if I gave you that problem and said to find the absolute extreme values, you would say, I don't have enough information.
That would be easy.
-2 to +3.
Thank you.
So you got it all? Okay, so try this problem. Okay, so when we take the derivative, this time we have this as 2/3 x to the 1/3. And you guys figured out there is no spot for this to equal 0. That happens. But what else did we have to check? Where it does not exist. So what would make the denominator not exist? 0. We want to know where would the denominator be 0 because it tells me where my function doesn't exist. So a critical point is 0. Just write it like that. And then you check your 3 values, f of 0, f of -2, f of 3. F of 0 was 0.
And then the next one is -1.587.
Good, use 3 decimal places. 0.80. Okay.
No, 2.0.
Now I saw a couple people just point at it and say this is the max, this is the min. If it were up to me, I would be cool with that. But on the AP test, if you just did that, they would not accept that. We need to make some sort of statement now. The max is 2.080, and again, sorry. We need to be even more specific. The max of what? F of x. We've got to start practicing this now so that we don't, I'm out of practice from last year because we haven't had to start being this specific yet this year. But we need to be that specific. We need to state that the max of f of x, I should have said the word of, is 2.080, and the min is -1.587. What if I asked you where the maximum and the minimum occurred? Where they happened?
So would that be just -2, 3?
It would be the x values instead of the y values. So again, another small difference. I could ask you what is the maximum, or I could ask you where did the maximum occur. Small difference that they like to try and trick you with. So homework.
That's a basic. I got so lucky.
Oh,